and get it into this variation of GIT. Okay. So I'm going to take C8 with coordinates P1, P2, x naught up to x5. I'm going to let C star act with weights 1, 1, 1, 1, and minus 2, minus 2. And I'm going to take W to be this O, to be P1, Q1 of x plus P2, Q2 of x. And this is C star. And the first GIT quotient is you delete x equals 0. And so you get the total space of O minus 2 squared over P5. And W is the function corresponding to the section of O of 2 squared that cuts out x. And matrix factorizations here is x. It's sometimes called Knurr periodicity. This equivalence is very easy. The other GIT quotient.
Yes. But in this case, when you build the resolution of the sheet, you take a sheet and build the resolution.
Yeah, you take a sheaf on X. Right, so it's the same picture. Here's your P5. Here's the vector bundle over it. Here's your X. You take a sheaf here and pull it up. It's something that it's in my notes, but I didn't end up saying. I could say maybe later is how to take categorical matrix factorizations that includes complexes of sheaves where D squared is multiplication by W. You also want to consider that. Just like you could just take you could immediately, in the old-fashioned world, replace all your sheaves with complexes of vector bundles. But that would be inconvenient for computation, right? And similarly here, with categories of matrix factorizations, you do want to consider complexes of sheaves where D squared is W times the identity. Or you could then resolve that, make a matrix factorization. Okay, I'll shut up about that. But what's the other GIT quotient? We're going to see something closely related to the curve. Other quotient. So you delete P1, or P0 is P1, call it P1 and P2, P1 and P2. 0. And so what do you get? Okay, you get the total space, well you get something over, it's like weighted P, well it's P1, right? But it's some orbifold P1. It's like weighted P1 with weights. 2 and 2. And the total space of O minus 1 to the 6. You could call it O1 and minus 2, but it's nice to do it this way. And so you get a bundle of C6 mod Z2s over P1. Let's put it that way. Let's say I map it to P1, and if I fix P1 and P2 not both 0, then what's the fiber? Well, you get a residual C6, but there's still this Z2 that acts. Right? Here's your P1. And you have each one of these is C6 on Z2. And we've seen that the matrix factorizations of on this C6 mod Z2W, that this is the derived category of 2 points. It's the Orlov category for the quadric where I fixed my values of P1 and P2, and I get some quadric. W of, maybe P1 equals some number, P2 is another number. So at each point of P1, with these coordinates, I plug in values, I get just a good old quadric, which is that, which is the one we considered before, and I get the overall category of matrix factorization. So that's like 2 points. Well, I should say the graded matrix factorizations of this thing, we said were derived category of 2 points, and the graded matrix factorizations of the singular thing are like D of a fat point. So that you're exactly seeing this double cover of P1 branched over the six points. So from this geometric story that was beautiful but a little bit ad hoc, when you put it in this GIT picture, it becomes a little more systematic. Or what if, or sorry, maybe I should take questions on that before I do the next one. What if X was the intersection of 2 cubics in P5? This is, by the way, a Calabi-Yau threefold. I don't have its Hodge diamond handy, I don't think. Oh, no, I do. Maybe I call it F1, F2 equals 0. So what changes here? So this -2 becomes a -3. This Q becomes an F. This 2 becomes a 3. And everything is fine there. On this side, I get a weighted P1 with weights 3 and 3. I get a bundle of C6 mod Z3s over P1. So this wants to be at the fiber. I have this bundle of categories of matrix factorizations, each one of which this wants to be the derived category of a K3. And so often you have Calabi-Yau threefolds that are fibered in K3 surfaces over P1. And often you have derived equivalences between 2 different Calabi-Yau threefolds. And so here you have an honest Calabi-Yau threefold, and here there isn't really geometry on this side, but what there is a fibration in K3 categories over P1. You could try to push it even further. You could say, can we get actual geometric K3s? Well, this K3 category associated to the cube fourfold is geometric. There's a real K3 there in a few cases. If the cubic has a node, or if it contains a plane, and then there's a Brouwer class, but we'll forget about that. Or if it contains a quintic Veronese surface, or an elliptic, a sextic elliptic ruled surface. There are a bunch of examples. And 2 of them were studied by Calabrese and Thomas. So Calabrese and Richard Thomas. John is postdoc at Rice. He's on the market this year. Should hire him. What if we say X contains a plane? And then this K3 is actually, now this is the derived category of some degree 2 K3 with some Brauer class that I don't want to talk about. Now the only issue is that now x, if x contains a plane, then it's singular. So you have to blow up the plane and get some small resolution. And over here you also have to do some resolution. That's a Brauer class bit. But after you do that, everything lines up beautifully. This Calabi threefold, it'll have Picard rank 2 after you blow up the plane, is derived equivalent to this one that's fibered in on its K3 surfaces. Well, but with a twist. And I'm sure they could have done the Veronese surface and so on, but they had finite time. And okay, so I've done pencils of hypersurfaces, intersection of two hypersurfaces, but you could take intersection of more quadrics, you could take intersection of more things of any degree, and so if I had an intersection of 3 quadrics, then you would get a double cover of P2 rather than P1 branched. Right? Because the category of matrix factorizations of each quadric is 2 points, and so you get a bundle of those categories of matrix factorizations over here, and you can make it all precise using this framework.
Is it always branched along the locus of singular quadrics?
Yes. Yes. And if you take 3 quadrics, sorry, if you take 4 quadrics, then you're going to get more singular elements of your linear system, and then you have to lose your mind a little bit. This is the subject of my thesis. So you can still find the geometry. But what Mark wants to know, like the reason I'm here, what if X is a cubic intersected with a quadric P5? Then what happens? Right, am I going to get something over weighted P1 with weights 2 and 3 that really should be thought of as a bundle? And so do we get a bundle of Landau-Ginzburg models? I'm going to stop apologizing for the word. Over weighted P1 with weights 2 and 3? Not really. Instead, something more exciting happens. And I've chosen concrete numbers, but what I'm saying is true of any, well, maybe I'll say the general theorem at the very end. Right, so what's the GIT setup? You let C star. Oh wait, no, I don't want to be in P5. I want to be in P4. Is that a K3 surface? Yeah. You agree that it's a surface anyway.
I was about to get very excited there when I thought it was in P5, because then it's just another one on this kind of finite, incredibly finite list of things of Hodge level 1. I thought you were going to tell me something interesting about.
Oh, I can. We can say something interesting about that one too, maybe.
Okay. Well, I'll let you actually give the talk.
Yeah. We might be able to say something interesting about that one. So C star acts on C7, P1. Let me call him P, Q. No, that's bad. P1, P2. P1. Sorry? C7?
Q can be quadrics.
Yes. X naught up to X4, and my W is going to be P1 times a quadric of the X's plus P2 times a cubic of the X's. So these weights had better be. But let me switch. -3, -2. So you delete x equals 0, and the same story, you get O of -2 plus O of -3 over P4, and then eventually On the other hand, if I delete P1 as P2 is 0, we get O minus 1 to the 5 over this weighted P1, weights 2 and 3, well 3 and 2. So maybe here's this weighted P1, and here's the point P1 equals 0, and here's the point P2 equals 0. And what are the stabilizers? Is it Z2 and Z3 or Z3 and Z2? Here I think it's a Z3 stabilizer. And here it's a Z2 stabilizer. Or I got it backwards.
I think when P1 is 0, isn't it negative 1x trivial?
P1 is 0.
Yeah, so here it's a Z2 stabilizer. Forgetting about all this.
Yeah.
Here it's a Z2 stabilizer, and here it's a Z3 stabilizer. Good.
But P0, the stabilizer P1 0 is 4
Yeah.
derived.
Forget about
This
the-
is C3 acting on the coordinate P1, right?
But P1 is 0. So P2 is
And
the
so
coordinate.
that's the stabilizers. Or maybe I'm confused.
Yeah, so this is the point 0, 1, and this is the point 1, 0. It's very confusing. Like there's no, you never stop being confused by this.
Yeah, right. So
Right, so the point 0, 1, as you say, minus 1x trivially. The point 1, 0, cube root of here dx trivially.
oh, -1. That's true.
Yeah, okay. And so we sort of have this bundle, right? Here we understand perfectly well. We have the fiber is this C5 mod Z3 related to the cubic, right? Here it's C5 mod Z2 related to the quadric. But what about in between? Right, what is that fiber about? And the answer is you shouldn't think about that fiber. And because you can have, I haven't talked about what the support of a matrix factorization is, but you can have matrix, because of, I'll say for Mark, because of R charge, that's the last I'm going to say about R charge, you can have things supported in this fiber or in this fiber or supported everywhere, but you can't have anything that's just supported in this blue fiber. Like it's not R invariant. And so, there's nothing that's only there. There are things that are spread out everywhere.
Sorry, just to make you say more.
Yeah.
Can you tell me what your R charge
Yeah,
is?
my R charge is, this is how you take care of all this grading. It's just, it's 2, 2, 0, 0. So now W has R weight 2. But this point is, this fiber is fixed by that action, and so is this one, but these blue fibers in the middle are moved by that action, so you can't have anything that's just supported there. Anything invariant. Okay. So instead, let's look at the open set. Where P1 is not equal to 0. So now I'm going to have C7, and I'm going to change variable. I'm going to substitute P2 with P2 divided by P1, which I'm going to call P3. I'm just going to call it P. I'm going to take chances and call it P. So now I have C7, right? Because if P1's not 0, I can divide by it with P and X naught up to, you know, I'm going to call it Y. That's what I'm going to do. That's this one. Z6 with those coordinates, right, modulo Z3. Right, and now these have weights 1 and 1. Right, so if I replace P2 with P2 divided by P1, that turns into weight 1. Now when I mod out P1, I'm just left with the Z3 statements. And this is exactly, this is Orlov's thing. So I'm looking at, or this is Orlov's C6 mod Z3 for the cubic fourfold y times q of x plus f of x, which has a node at the point 1 and then a bunch of zeros. And similarly, any cubic with a node at that point can be rewritten in this way. Right, so if I delete this fiber, then what I'm left with is a big open set, which is exactly Orlov's Landau-Ginzburg model for a singular cubic fourfold. And this agrees with something that Kuznetsov already did, was that D of the nodal, now he proved it in a very different way. This is, you have some category, well, let's say it this way, that the matrix factorization category of a nodal cubic fourfold has some, so this D of X is a categorical Krebs resolution. And the map, which is like the push forward from the resolved thing down to the singular thing, is you take a matrix factorization on this whole big red picture and you restrict it to the green open subset. That's the push forward. And you can do this with any set of numbers. Maybe I'll throw some more numbers in your face before letting you go. So similarly, if X is a cubic with 2 quadrics in P6, which is a Calabi threefold, then you get, this is a categorical resolution of the category of the Orlov category of matrix factorizations for a nodal cubic sevenfold. We've seen that for a smooth cubic sevenfold, this is a Calabi CY3 category, but it can't be geometric. But the point is you degenerate to a nodal one and then you can resolve at some sort of extremal transition. You know, with Calabi threefolds, you're always degenerating to a singular one and then taking a small resolution. Well, here we're taking, there was no geometry, there was just this category, but we can degenerate it to a singular one and then resolve it this way. Or you can end up, maybe I won't write it, if you do a quartic and a quadric in P5, then you end up with a quartic in some weighted P6. And so there's any numbers you care to write, you're going to end up with a categorical resolution of singularities in this way. I don't promise that it'll be Kreppin most of the time. Would you? Yes.
Sorry, what's it mean to say a categorical resolution?
I guess it means that you have a functor this way that acts like push forward, and a functor from perfects here to that acts like pullback. So in this picture, perfects would be things that are supported, that are compactly supported. And so you can include them into the bigger space that satisfies whatever you would want from push forward and pullback by a resolution of singularities. Is that what I wanted to say? And again, to continue talking to Mark for one more minute. Here you see, you remember my talk in Michigan, you had a resolution of singularities where the critical locus of your superpotential was the Calabi-Yau, the nodal quintic that you wanted with a line sticking out. And then you compactified it by sticking a point at the end of infinity there. And you got a resolution of singularity. Similarly, here you have what you want, which is the origin, with a line sticking out. And then you compactify it, and now you have a resolution of singularities. So, I think that's what I wanted to say. That you should take this GIT picture for whatever complete intersection you like. And if your biggest degree only occurs once, I should say, yeah, if we had 2 cubics and a quadrant, we'd be in trouble. But a cubic and 2 quadrants is okay. Then you see your smooth thing resolving, there's a higher dimensional singular thing by taking it up in 7.